Hello ladies and gentlemen, I'm Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to talk to you about another one of my articles. This one is entitled X9 Solar Flare and the Extremely Active Sun. Now, on September 6, 2017, an intense solar flare was released by sunspot AR2673 at 12:02 UTC, or at 8:02 EDT. Now, we can see images below. From the first one is from 1228, where we can see that an extremely intense solar flare was released. You can see how bright it is. So it happened at 12:02. At 12:28, the radiation was still seen coming from this area. It does take 8 minutes for the radiation to reach Earth, and as we can see, very intense and very bright. This is in the 13.1 nanometer or 131 angstroms. Sorry, that's a mistake, it's not X-ray. This is ultraviolet radiation. This one is in X-rays. This is in 9.4 nanometers, and this is from 1230, and again we see the great intensity of the solar flare. So I could see already from this graph that it was X9 at least. It was later classified as X9.3. Now we can see from here, this is the time, September 6, 0, 3, 6, 9, and 12. So you can see it happened at around 12. And the red line is the GOES 15 satellite data. And we can see it goes straight up, almost right to the top. And here we can read what classification we have. So this, if it had gone up to there, it would have been 1. So that would have been X1. So 2, 3, 4, 5, 6, 7, 8, 9. So it goes right up to the top, and so it's an X9 solar flare, extremely strong. Now, the solar flares are due to the release of energy from the sun's magnetic field when a magnetic reconnection occurs, and it occurs in the inner plasma loops associated with sunspot groups. And the magnetic fields are very intense within sunspot groups because they are very close together, they push very close together, they come out of the north polarity sunspots and they go in through the south polarity sunspots. And these lead to magnetic reconnections. But we can also see, because of the release of X-rays, that the surface temperature of the photosphere is actually higher than 6000 Kelvin, because thermal X-ray photons are indicative of temperatures of millions of degrees Kelvin. This energy is not always available because of the motion in the plasma in the photosphere. So this energy goes into giving the plasma kinetic energies. They're not available to release X-ray photons. It's only when this kind of explosion occurs that the kinetic energy is transferred to thermal energies, then released as X-ray photons. So we can see here, this is not the latest image, this is from August 26, 2017, but it contains a plot of the magnetic field lines around the sunspot group that was at the time facing Earth. And the image is in 17.1 nanometers. But what's important is that you can see the magnetic field lines and how close together they are within the sunspot group. This means the magnetic field is very intense in this area, and the magnetic field lines will then push against each other, will be pushed upwards, and will lead to magnetic reconnections happening. And we can see here an illustration of how these magnetic reconnections happen. This is a sunspot group, a north polarity one, the magnetic field lines come out of it. There is a south polarity one, the magnetic field lines go inwards. These are the loops connecting the two. There will be particles spiraling along these, which is why these will look like plasma loops, because of the hot plasma moving along these magnetic field lines. Then the magnetic field lines are pushed upwards. They start pinching, the inner ones start pinching, they get close together, and eventually a magnetic reconnection happens, which is it releases an explosive amount of energy, and this energy is released as thermal photons, in other words X-rays, and it also accelerates the ionized particles that were in the area, and these particles are accelerated to extremely high velocities. They are relativistic and therefore cosmic radiation particles, although for the sun they're usually called solar energetic particles. And so we immediately get a very high intense radiation being released. It will take 8 minutes to reach Earth because it travels at the speed of light, and after that will come cosmic radiation, which will take 30 minutes or more. Well, the most energetic will take about 30 minutes, and after that more will come that is not as energetic. And the cosmic rays go right through the magnetosphere. They will cause showers of secondary particles, and we will get neutrons, pions, muons, electrons and positrons, and gamma rays. And the gamma rays and pions and neutrons can reach the surface of the Earth, and these are highly energetic particles still, and very damaging to living organisms, and can lead to cancer and death if the radiation is high enough, or if there is enough of them that reach the Earth. So they are damaging to living organisms. And they will also ionize the ionosphere. So it will induce currents in the atmosphere, so there will be large changes in current flows in the ionosphere as a result of both the electromagnetic radiation and the cosmic rays impacting the Earth's atmosphere. And these in turn will induce currents further down in the atmosphere, on the surface of the Earth and inside the Earth, and these currents will increase the severity of storms, interrupt communications, lead to power surges in power lines and transformers, which in turn can lead to power failures. And the currents that are induced inside the Earth heat up the magma, and these lead to increased earthquake and volcanic activity. So usually within minutes of a CME being released or solar flare being released, we start seeing increased earthquake activity. Now, the impact of a solar flare can also heat the upper atmosphere and cause it to expand. However, a CME, when it impacts, it increases the particle density at the magnetopores and compresses the atmosphere, and can even lead to cloud formation at lower altitudes. Now, the fact that we are getting X-class flares at a time when the sun is supposed to be moving towards a solar minimum is just not normal. The sun is getting more and more active and unstable. This is most probably due to the large numbers of stellar remnants congregated in the sun's corona, which are weakening the sun. I have written extensively about these objects. They are old stars, and they connect via their very high magnetic fields. They make magnetic connections with the sun. They draw plasma from the sun. They weaken the sun, and it may lead to the sun releasing solar flares because they pull on the sun's magnetic field. And a weakened sun is also more prone to going into the red giant phase. This is what happens to stars when they run a bit low on energy and they start aging. They start having trouble holding on to their plasma, and this causes the outward expansion of the star, whilst the ionization layer of the photosphere moves inwards towards the core. And this is what we see illustrated here. As a star starts aging process, the ionization layer or the photosphere will move inwards towards the core, and it is still an anode. It has an electric field which is outwards, which accelerates particles away from the center of the star. And so under the action of this electric field, the outward layers of plasma are moved outwards, and so the star seems to expand. But it is actually weakening, and its ionization layer is moving inwards, and eventually it moves right to the surface of the core of the star, at which stage the star becomes a white dwarf. And after that it continues to lose energy. Eventually it cools down and is only able to emit infrared radiation, at which point it becomes a brown dwarf star, or what I nowadays call stellar cores or stellar remnants. They are mainly the core of the star with some plasma around it, and this plasma, I have discovered, is not even in the gaseous phase, is in the solid and liquid phase. This seems to be the case even with the sun at the stage that it is right now. So a star stops the outward expansion of plasma through its magnetic field. If the magnetic field moves inwards or weakens, it leads to an outward expansion of the star or its outer layers of material. Now, sunspot AR2673 is a very complex sunspot group. Its magnetic classification is beta, gamma, delta. And the beta gamma means that it's a bipolar magnetic classification group. So it has positive and negative polarity sunspots, which are clearly discernible. But it's complex in that we cannot draw a clear line between the positive and the negative. They are basically mixed in the regions where they occur. The delta is due to both positive and negative polarity umbrae appearing within one penumbra. And we can see here, this is sunspot AR2673. This is a magnetogram. This is the visible light image of the photosphere. We can see the sunspot. The sunspot is the dark area. This is the black is called the umbra. The dark orange is called the penumbra. That's the region that surrounds a sunspot. And here in the magnetogram, we can see the positive and the negative regions. The blue is the positive polarity sunspots. The red is the negative polarity. And the penumbra, we have in the penumbra, the yellow is the negative, the green is the positive. And it's a delta because we see two umbra here, one negative, one blue within one penumbra. So it's surrounded by one orange region. So this means that the magnetic field is very intense, and this sunspot group is therefore prone to strong solar flares. Now the classification, I've put some of the possible classifications. We have the first one is alpha. This would be a sunspot group that only has one type of or one pole, only north or north or south, or we can say positive or negative, but it's unipolar. It's only one pole in one group. And then we have the beta, which is a bipolar or two opposite poles. The north and south polarity would then be clearly visible, and we would be able to separate it by a line. In other words, there would be north on one side and south on the other side of that line. We would then move to beta gamma when it's also bipolar. That is, we see negative and positive, but we cannot draw a line separating them. They are mixed, and as we see has happened here with AR2673. We try to draw a line right through the center there, and we can see we have some positive then on the side here where there is negative. So it's mixed and complex, and therefore we would call it a beta gamma. And then we would add the delta, and that refers to different polarity umbrae within the same penumbra. So this is what happens here as well. Now, the region surrounding sunspot group AR2673 was observed to be venting for quite a while from September 5th, 2017. And we can see that in these SOHO-LASCO C2 images. And these are from September 5th, 1536. We can start to see some venting coming out from that region. It seems to be increasing as time goes by. This is at 1648, and this 1548, 1656, and as time goes by, there seems to be an increased venting and possibly a release of a CME here. And this is from the 6th, from about 8 o'clock. This is 10:12, 10:36, and we can see it looks like a CME is being released. And but this is strange because this is before the solar flare. Also in that image we start seeing something that looks circular and solid. It's indicated here. This is the same image from September 6, 2017 at 10:36. We can see a circular, and it seems to be a solid object moving ahead of the CME. And we can see the object again. It remains as a circular object. It doesn't change shape, therefore looks like a solid object, and therefore a stellar core moving away from the sun. Then we have the CME. This is the last image that was available. This was from September 6 at 12. This is 2 minutes before the solar flare occurred, and we can see it definitely looks like a CME is being released from the sun. And this is very strange because a CME usually is seen coming from the sun after a solar flare, not before. We can also see it seems like some activity on the surface of the sun. This occulter is not a physical barrier, it's actually a digital barrier. So sometimes we see objects and activity at the sun's surface right through it. And this seems to be the case here. Then we look at the LASCO C3 images, and again we see a solar flare seeming to be coming from behind the occulter from about 1106, and we see it developing there at 1154, definitely before the solar flare at 1202 UTC. So we can see it here. This is the occulter occupies the space from up to 3.5 radii from the sun. So this is the solar flare. I mean the CME was already beyond that point at that time. Now the same thing happened on September 4th. There was a large CME on September 4th. You can see it here. Quite a large CME at the time. The sunspot was Earth-facing, AR2673, and so the CME seems to come out from every direction from the sun, but it's because the sunspot from which it came was Earth-facing. And we can see this happened way before 2018, and yet the strongest solar flare it could have been associated with, the M5 solar flare here, happened at 2033, so a little time after. So this is very strange that we are getting solar flares after CMEs. It's supposed to be the other way around. But this is indicative of stellar cores or stellar remnants pulling on the sun's magnetic field and causing increased activity. They are causing the sun to vent, the sun to have CMEs, and then eventually it seems to eventually cause solar flares. So This is, however, still strange. Now, these brown dwarf stars or stellar cores close to the sun and in the sun's corona connect magnetically. With the sun, they pull on its magnetic field. They cause particle flux transfers with the sun. So it's not surprising that these connections lead to fast development of sunspots and CMEs. They also weaken the sun, thus making it unstable and causing it to have more difficulty holding on to its surface plasma, leading to stronger CMEs and CMEs that would not be happening otherwise. And this is the diagram that I usually use to describe and illustrate what actually happens and how these objects connect to the sun. They do not seem to connect gravitationally at all. We can often see in these objects that look like they might be more massive than the sun, moving slowly away from the sun. If they were gravitationally attached to the sun, they would either quickly collide with the sun or go into a very fast orbit, or they would cause the sun to go into a fast orbit around them. But this is not what happens. They connect magnetically and magnetically only, not gravitationally. And they pull the sun's magnetic field lines because these objects have very high magnetic fields towards themselves. And these magnetic field lines then seem to be open. This would then cause a coronal hole as particles from the sun spiral along these magnetic field lines towards the object. Then plasma from the stellar core spirals along the returning field lines towards the sun. Thus, this object obtains high energy plasma that comes from the sun, whilst the sun gains low energy plasma that comes from this object. And this, of course, weakens the sun and rejuvenates the stellar core. Now, you have to remember the magnetic field lines always have to form closed loops. So this is why this sort of thing has to happen. These field lines are never open. They may be described as open, but they must close somewhere. They close inside the stellar core and return, causing this particle flux transfer between the two objects. So, in conclusion, stellar remnants in the sun's corona are increasingly causing the sun to vent plasma. They are destabilizing the sun and causing increased solar activity. It is also possible that the sun is about to enter the beginning of a red giant phase, as it seems to have increasing difficulty holding on to its surface plasma. Either way, this is caused by these objects weakening the sun and drawing on its plasma through their magnetic connections with the sun. The Earth's magnetosphere will be under increasing pressure due to the resulting solar flares and CMEs. I am Dr. Claudia Albers, Planet X physicist. Thank you for watching.